Hello, and and anyone else who may join, welcome back to the Technoteach virtual course. Last week you were going over the assembly language and the little man computer with Alex, and you've done that for the past 2 weeks. So hopefully you've got an idea now of how yeah, assembly language and machine code works, how our high-level programming languages, as we've been doing for several months now, such as Scratch and Python, how they are translated into those low-level languages that the machine itself can actually understand, and the complexity that that adds as you go lower and lower toward machine code itself, which is obviously mostly, or arguably entirely these days, in in binary. Um, so that's what we're going to be looking at over the next 2 weeks is number systems. We're going to mainly, or entirely rather, focus on binary, decimal, and hexadecimal number systems. These are the three that are primarily in use within computer science and technology these days. Um, Interestingly, throughout the years, there have been computers built in other bases in other number systems, um, but they were more, pioneering, I guess, experiments of the 70s and 80s when computers were a very new idea and trying to build a computer that could work in a different base, say. Whereas because of the way technology and electronics works, as we are going to go through now, binary is essentially what all machine code uses. It's very easy for a machine to understand binary and build a machine using binary. Uh, Decimal is, as I hope everyone is aware, the number system that we use generally as people. Most of our day-to-day maths is done in decimal, okay, because we've got 10 fingers, makes it nice and easy to count. And so that's what we're taught from when we're very young, counting from 0 to 9. Okay, we got a base 10 system, so we have digits between 0 and 9. And hexadecimal then goes up to, well, 16. So you've got digits from 0 to 15, which we'll have a look at how exactly that works during this session. So from the new GCSE comp sci specification, which do bear in mind is going to be updated now in September. So there will probably be some changes to what we've learned over the past year. However, I very much doubt that something as basic and core as number systems will end up changing in any significant way. Still a very important thing to learn. But yes, we will run an updated course next year if anyone has any interest in attending again or signing up to that. Just to put that out there now, nice and early, as we've started discussing it this week. However, yes, from the current GCSE spec, we are going to learn how to use and convert between denary, binary, and hexadecimal counting systems. Okay, we're not going to go too complicated with binary. The spec only asks you to be able to do it up to 16 bits. The reason it asks you up to 16 bits is important, as we'll get to during this session. So we're going to learn how to do direct conversion of these bases and using intermediary bases as well. However, that part may fall into next week's session. We'll explain the use of hexadecimal notation as a shorthand for binary, why that is done, and why we use hexadecimal in computing when, as just mentioned, all computers work in binary. So why do we decide to complicate it with hexadecimal? And we learn how to use arithmetic shift functions and be able to explain their effect in the number systems. Okay. And then we'll apply binary addition techniques, learn how to add, divide, and get the remainder of binary numbers, and explain the concept of an overflow. What are overflows? Why do they happen? And so on. So if anyone is completely new to binary or not very confident at all, then we know that computers use binary the digits 1 and 0 to be able to store data. And therefore, a binary digit, a single bit, as we call it, is the smallest unit of data in computing. So whenever you hear bits, they are talking about a single binary digit, either a 0 or 1, either on or off, either true or false. Okay, we looked at this previously with Python, and I think we may have even touched upon it in Scratch, the idea of these true, false, on, off, 0, 1 concepts. And that really takes its core in binary. And therefore, binary numbers are made up of binary digits. So, i.e., the number 1001 in binary is 9 in decimal. And so we'll have a look at why that is. Now, transistors. That's what makes a computer work. It's what makes any modern technology work. We have 3 legs on a transistor. We have our base, and then either side of that, our emitter and our collector. Our collector takes an incoming signal. Our emitter emits that incoming signal, but only if there is a signal from the base. So that essentially makes a transistor an electrical switch. It can be on or off depending on whether there is a signal being transmitted to the base. So by grouping a lot of transistors together, we can make a lot of electrical switches that will switch on and off with a signal. So when the signal is 1, a binary value of 1 is transmitted to the transistor, then the transistor lets current flow through it. However, when a binary value of 0 is given to the transistor, then nothing flows through it. So this seems relatively simple. Okay, we've just got a little electrical switch that can let electricity flow through. However, as we add billions of these transistors together, we can actually build very complicated systems. And this is how every modern computer works. Billions of transistors working together to transmit binary signals through circuit boards. And when those binary signals are sent in some sort of meaningful order, we can decode that order, and we can get processes running on our computer, and we can build quite complicated systems through controlling the bits that are able to flow through. So with a bunch of transistors, we can build up a longer string of binary numbers. For instance, the binary number 11010010, which would be 210 in our everyday decimal systems. Now, this links into other subjects. So when computers were first being developed, then the data into these computers had to be entered either via punched cards, were very popular in the 50s and 60s, as well as flicking switches, or pushing pins into the computer itself. So actually connecting, adding something that the electricity could flow through. You are completing the circuit with a pin. And famous examples of these old analytical machines are Charles Babbage's analytical engine from 1837, which you can see there. The first uh, proper built computer that could do multiple mathematical operations depending on how it was programmed. And then our punched cards um, that we used to program this analytical engine. So it accepted punch cards into it and would run different programs depending on where the holes were in those cards. And then the Colossus Mark II, which was operated during World War II, and how we ended up cracking a lot of the German encryptions were by this larger machine. And you can see there what I mean with the pins and switches. You can change the inputs into this computer. You can reprogram it and give it different data by switching the pins. So these don't look like modern computers. They, they in the first one, there is no electricity flowing at all. It is a mechanical machine. However, it uses the exact same concept of binary digits switching. Okay, we have uh, we have a machine that can turn on and off, turn different parts of its program on and off, depending on the inputs given to it. And so instead of programming it with, we forget high level languages like Python for now, okay? Instead of using machine code like we did last week and the week before and giving it those ones and zeros directly to control its processes, okay? A certain pattern of ones and zeros means that you add two values together. Another pattern of ones and zeros means that you print them to the screen. Instead of using this modern electrical technique, all of these ones and zeros in the analytical engine were mechanical, okay, making cogs turn and cogs attach to each other in different ways, depending on the inputs that were provided to the machine. And then in the 40s with the Colossus, depending on the different pins plugged into the computer, directly changing the electrical wiring of that machine, changing the way the circuits connected to each other, allowed different programs and different data to be given to that machine. The exact same concept, but in a much more manual way. Not a complete architecture that we have built now. Okay, your computer's CPU never changes. You never go and have to switch out transistors inside of it. Everything is done by the computer by running different electrical signals through it. But all the same concept of switching binary bits to get different programs running. So we mentioned bits. A bit is a single binary 1 or 0, but we group our bits together to make them easier to work with. So when we have a group of 8 bits together, we call that a byte. We've all heard of bytes plenty, and that's what a byte is referring to. It is 8 bits of binary information. And why it is 8 bits of binary information, we will get to momentarily. However, maybe interesting to you that there is also such thing as a nibble. Never gets mentioned much, but a nibble is half a byte, 4 bits long. And then we have a kilobyte, which is 1024 bytes, or 1024 times 8 bits. A megabyte is 1024 kilobytes, or I can't even read that number. 1,048,576 bytes. A gigabyte is 1,024 megabytes. Terabyte is 1,024 gigabytes. At least this is what we're taught when we're young. And I was also taught this. I remember this information. And it is, I believe, still in the curriculum. It is what the WJC puts in their curriculum. And these are the numbers to learn. However, what may be interesting to your learners, though won't come up in exams, um, but is an interesting topic of discussion, is that this isn't necessarily true anymore. In fact, since the 90s, the I always forget their name, the International Commission of Standard Units, whatever they call themselves, that standardize um, units of measurement. Um, they, as part of the big push toward everything being metric, um, they they pushed for this to be changed in the late 90s, and it was agreed on and adopted. We should be measuring our bits and bytes in powers of 1,000. So a kilobyte is 1,000 bytes, a megabyte is 1,000 kilobytes, a gigabyte is 1,000 megabytes, and so on. Um, However, it's hard to enforce that. And so a lot of computing companies never stopped using the old method. And there's a reason for that. Because I'm sure you have all at some point in your life gone and bought a nice new, I don't know, let's say 16 gigabyte memory stick, and you've brought it home, you've plugged it into your computer, and it's told you there's 14.9 gigabytes free on the memory stick. And you're like, well, that's not 16 gigabytes. Have I been lied to? You have, because what this company has done is they have printed on their box that there is 16 gigabytes using the 1024 method of conversion. And 10,024, if you multiply that out all the way down to bits and then re-multiply by 1,000 all the way back up, then gigabytes using the 1024 method is actually 14.9 gigabytes using the 1,000 method. So companies artificially inflate the sizes of their devices by claiming that they are a gigabyte. And if they ever were to be argued with against that, they would just claim that they're using this other method of conversion, which is not illegal. So you find that actually happens a lot. It doesn't tend to happen when you buy nice contained devices that already contain everything inside. For instance, let's say if you go and buy a new iPhone and they tell you it's 250 gig of storage, it is 250 gig of storage. And that's true for many companies. If you buy nice expensive hard drives, that's also true. Okay, Seagates and Western Digital, those massive companies, they give the correct 1,000 conversion amount. However, one controversy recently surrounding this was the PlayStation 5. When the PlayStation 5 shipped, it only had a hard drive of 825 gigabyte, which people thought was a bit small for a brand new modern console. Okay, we're up to computers and things having several terabytes of storage now. So the PlayStation 5 shipped with not really all that much. Um, and then that really infuriated people when they got home, plugged in their PlayStation 5, and it told them that there was actually only 670 gigabytes. So over 150 gigabyte of that storage had disappeared. Um, and the reason for that is this conversion. Um, this conversion rate meant that the PlayStation actually had a significantly smaller hard drive than was advertised. Um, but anyway, that's not necessarily something that's on the curriculum, just quite an interesting piece of history. Okay, so what is the amount of storage required for different things? We hear these numbers a lot, but we don't necessarily think about how much files actually take up. Well, a single ASCII character of a text file. Okay, ASCII is the standard encoding for characters in all your texts. Um, and they take up 8 bits per character, which gives you an awful lot of characters that can be used. So that's how we end up with, the English alphabet and the Cyrillic alphabet and the Hebrew alphabet and so on, because each character is taking up 8 bits of information. So 1 byte per character. So if you write the word Monday in a text document, that document in theory should only be 6 bytes. If it is just a plain file with no sort of extension after that, if it's not a Word file that says .x or .docx even, if it is just a standard empty file that you can make in Notepad, then it should be 6 bytes. A plain text email measures around 2 kilobytes. A 64 by 64 pixel GIF, so a nice small bad quality GIF that we're all used to seeing get text to us and things, is 12 kilobytes. A nice high res 2000 by 2000 pixel photo, the sort of thing that your camera might output, is 11.4 megabytes, so 12 megabyte essentially, where that's 1,000 times bigger than the 64 by 64 GIF. A 3-minute MP3 audio file is 3 megabytes. 1 minute of uncompressed WAV. A WAV file, if you're unfamiliar, stores the raw wave of sound. Instead of encoding the sound to just be played via like MP3, where all the information's encoded inside of it, a WAV file actually stores the wave that will be played. So that's quite a bit bigger at 15 meg. And if we compress an hour-long film down to MP4, then that will come out at about 4 GB. This is from BBC Bite Size in 2017. For reference there, MP4 is a nice compression standard that really cuts down on our film sizes. Your average Blu-ray disc is about 80 gigabytes in size. So a Blu-ray film, a high quality HD film, could be up to 20 times the size of that MP4. Okay, so that's all about bits and bytes, how this information is stored within a computer and how many of those binary bits are actually needed to store these pieces of information. Okay, if we step back a sec, your megabyte is over 1 million bytes in size, which means it's approximately 10 million bits in size. Okay, so a 3-minute MP3 file, your average 3-minute song, requires the transistors inside of your computer or your MP3 player or your phone to flip on and off approximately 30 million times. There's quite a lot of information stored in us in our everyday lives, in the things that we use. And so our computers are equipped to deal with these massive amounts of data and running them at incredibly high speeds. Okay, your average processor in a modern computer works at several gigahertz, meaning that it can flip a transistor on and off about 1 billion times a second. Incredibly fast. Okay, so all our computers use binary, 0 and 1s. However, everyday life, we use the numbers 0 to 9. This is decimal or denary or base 10. Any of those names are fine to describe it. So a number base tells us how many digits are available in that numerical system. So in denary, decimal, base 10, we have 10 digits that we can choose from. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 digits. In binary, we've only got 2, 0, 1. And everything has to be translated into those zeros and ones. and we'll get onto hexadecimal in a bit. So all denary numbers have a binary equivalent, and it's possible to convert between these two bases. And to do this, we need to break down the numbers into their place values. In fact, every number system has a decimal or binary equivalent. Any number system can be translated between using the methods that we're going to go through today. Okay. There's an infinite amount of number systems. Okay, you could choose the base 1 billion if you wanted to, and you could have a billion different symbols that you could write down. And only when you got to the number 1 billion would you have to write your second symbol. Being incredibly impractical, but you can make a base out of any number. Okay, using the denary system then, 7,242 reads exactly as that, 7,242. But we can break this down. We can simplify it. We know what each of these mean. It means that we have 7,000s. We have 200s. We have 4 10s, and we have 2 1s. And we can take these numbers and place them in their columns. Okay, we all did this in primary school. We all remember how to break down a number into ones, tens, hundreds, and thousands. And so we can do this with any of our number systems. Okay, we can break it down into each individual unit. Now, in denary, in decimal, we have 10 different values, 10 different numbers, symbols that we could place in the ones category. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 that could go in the tens, 10 that can go in the hundreds, 10 that can go in the thousands. So each time we are multiplying by 10. Okay, we have 10 to the power of 0, which is equal to 1, our ones. We have 10 to the power of 1, which is our tens. 10 to the 2 is our hundreds. 10 to the 3 is our thousands. We're going up by 10 each time because this is decimal. It is base 10. Similarly, we can break down a binary number into its individual columns, but instead, we now have to work with a power of 2 because binary is base 2, which means there are 2 values that can fit in the ones column, 0 or 1. There are 2 values that can fit in the twos column, 0 or 1. There are 2 values that can fit in the fours column. And there are 2 values that can fit in the eights column. Because just as with 10, we have 2 to the 0 is our ones column. 2 to the 1 is our twos column. 2 to the 2, 2 squared, is our fours column. 2 to the 3, 2 cubed, is our eights column. So any number we can break down just like this, and we take our 1, 0, 0, 1, and we go, right, how many ones do we have? 1. How many twos? 0. How many fours? 0. How many eights? 1. Okay, 1 times 8 plus 1 times 1 equals 9. So we can break down any number using this method. Okay, and there, it is important when we're using binary and other systems that we refer to this number as 1001. We should not refer to it as 1001 because it is not 1001. The number 1,000, the word 1,000 is unique to our decimal system. Okay, we don't have 1,000 in other number systems. 1,000 is a multiple of 10. It is 10 times 10 times 10. It is unique to decimal, and so we should be very careful of referring to these numbers any other way. Okay. Okay. So We can also use this same system to calculate larger numbers. Okay, if we've got 101010000, we split it into the columns. We just write it out in powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. We multiply by 2 each time, and we fill in the number. And then to get the answer out, we look at our at each number and we go, right, 1 times 128 plus 1 times 32 plus 1 times 8 plus nothing. 122, 128 plus 32 plus 8 is 168 in decimal. Okay, for a moment, um, I've got some numbers that you can try converting using this system. So remember, just write out the powers of 2. You've got the ones column, the twos column, the fours, the eights, the 16s, and so on. And I'll pause there and give everyone a moment to type that out. Oh, thank you, Anna. And I just saw your reply on the chat. I had a feeling that you wouldn't be allowed to say 1,000 bytes in Digitech GCSE. I had a feeling they'd be fussy about that one, um, which is fair. I can understand that. I think it's important to learn the 10 to the 24 as well. I think that's an important piece of history, if nothing else. Well, it is still used, so it's not just history. Um, but yeah, generally it should be using 1,000. Um, if you just want to give me a thumbs up when you work those out, Dan, I'll give you time to complete them, as you're the only one here, and yeah, then I'll carry on once you've had a go. Fair enough. Fab. Yeah, well done, Anwen. I believe they're spot on. The first one is 14. 1, 2, 4, 8. So that's 8 plus 4 plus 2, 14. Um, Second one goes up to 16 here, but there's 0 in the 16 column, so it's relatively pointless including it. It would be like writing the number 0012 to represent 12. We know it's 12, you can leave out the zeros. Um, and then the second one is 29. Um, this one is 65 because we go up to 64 here. There's a one in the 64s column, and there's a one in the ones column is 65. And then a nice trick to work out a really big one like this, which is 1, 2, 3, 4, 5, 6, 7, 8 long, is to work out what number 9 would be, which would be 256 in the ninth column, and then minus 1, because 256 would be 100000000. So 255 is 8 ones. Um, and funny you should say that in the chat just now, Anwen, about running out of fingers. So you needed a calculator. If anyone is familiar with the comedian artist Tom Lehrer, that was really big in the 60s. He has a fantastic joke in one of his songs where he states that counting in base 8 is just like counting in base 10, really, if you're missing 2 fingers. Because it is. Okay, the reason we count in base 10 is because we have 10 fingers. We can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Makes it nice and easy as a counting system. If you have 8 fingers, you would only be able to count in octary. You would count up to 8, and then you'd have to start again. You'd be on the 10, or not the tens column, you'd be on the eights column. So you then count up to 64 in the eights column. And interestingly, with number systems, I'm getting way off topic now. But there are many cultures in the world who didn't use denary, didn't use decimal. That was a very Western European thing that evolved, using decimal. But particularly the Mayans or the Incas, I believe it's the Mayans. Um, uh, they obviously had their celestial calendar that everyone thought meant the end of the world in 2012. Um, but they actually counted in base base 16, I believe. And what they counted on were the quadrants on each finger. So they would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, no, maybe it was base 12. Yeah, they'd count in base 12, and then they'd use their thumb to start counting in the 12s column. So you'd count up to 12, and then you'd add one on your thumb, and then you'd count again. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And you add another one to your thumb. So you can count up to 36 on one hand if you use the Mayan system. Number systems are very interesting. But yeah, anyway, back to binary. So nice and easy, just using the columns method there. Okay, 1, 2, 4, 8, 16 is all you need for GCSE. After that, you just keep multiplying by 2, 34, 32, 64, 128, 256, 512, 1024. That's where that number comes from in the gigabytes. 2048, and so on. So using that column method to separate out your binary number makes it super easy to convert from binary to decimal, because you just add up each of the numbers that has a 1 in the column. However, converting denary back to binary there are two primary methods that we can use to do this, and we will go through both of them. It doesn't matter which one you use. It doesn't matter which one you teach. It doesn't matter if you teach both of them. In fact, when we teach this as a workshop or when this is taught to students in university by us, we do teach both methods because people think in different ways and both methods have their benefits. And yeah, we'll go through them both. The first method is repeatedly dividing by 2, and we use the remainder to get our value. The second method involves repeatedly subtracting the biggest 2 to the n value that you can from the number. And remember, to check that our calculations are right, we just convert our answer back into denary, okay? We've just done that. It's super easy to convert from binary to decimal. So to double check your answer, just convert it back the other way and make sure you get the same number. Right, so if we were to convert 83 into a binary number using method 1, which is the dividing by 2 method, then we take the number 83 and we divide it by 2. We can't, it's an odd number, so we get 41 and a remainder of 1. Then we take 41, we divide it by 2. Can't, it's an odd number, so we get 20 and a remainder of 1. We divide 20 by 2, we get 10, remainder of 0. 10 by 2, 5, remainder of 0. 5 by 2, 2, remainder of 1. 2 by 2, 1, 0. And 1 by 2 is 0, so that gives us a remainder of 1. And then, to get our binary answer out, we read those numbers in reverse. So 83 in binary is 10100011. And that method does work every time. You'd hope all these methods work every time, to be honest. But I remember the first time I saw that method, it was a bit surprising to me. I didn't expect that to actually work out so nicely. But it does, works perfectly. The bit that you have to remember is to read it in reverse, because a lot of people end up reading it downwards, and that gives you a completely different number. But as long as you read that number in reverse, that works perfectly. So there you go. There are 3 numbers for you to test using the divide by 2 method. So remember, divide by 2 every time. If there's a remainder, write it down. And then divide the number that you got by 2 again. And repeatedly do that all the way down. Read the number in reverse. Okay, I'll give you a few minutes to do that. Okay, what numbers did you get out with that one then, Anwen? Looking a bit off. I think you've added a zero in with that 28. Um, so if I just add a text box for here, um, and I could do that one along with you. So 28, select the tabs. Um, we're going to start with 28. And then we divide 28 by 2, which gives us 14 and a remainder of 0. Then we divide 14 by 2, which gives us 7 and a remainder of 0. Then we divide 7 by 2, which gives us 3 and a remainder of 1. Yep, that's correct. Then we divide 3 by 2, which gives us 1 and a remainder of 1. And then we divide 1 by 2, which gives us 0 and a remainder of 1. So the number we should get out from that one is 11100. So 1, 1, it doesn't like tabbing for some reason. 11100. Which if we think of that in terms of columns, fab. Well done for getting them. So in terms of columns, sorry, I'll try and make that a bit clearer what I'm trying to say. So that's our binary. And then our values would be on the far left, we've got our ones column. Then we've got our twos column. Then we've got our fours column. Then we've got our eights column. Then we've got our 16s column. So how many ones do we have? 0. How many twos do we have? 0. How many fours? We've got 1. Got 1 8 and 1 16. So 16 plus 8 is 24, plus 4 is 28. So that gets us back to the same place. Okay, the bit that's important to remember while doing this, the bit that can really trip people up, is remembering to divide that 1 at the end as well. Okay, you still need to divide the 1 by 2 to get that final remainder of 1. So this method works nicely. However, it is quite a drawn out method. It's a lot of writing things down and just depending on the learner, depending on how your mind works, that's either going to go brilliantly or you are going to trip yourself up maybe by writing too much. So the other answers I got for 43 were 101011 and 99 is 110011 and they should all check out. Um, so that is the first method for doing it. The second method is subtracting the largest 2 to the n value that you can. So if we take the number 84 and we want to turn that into a binary number, then we go 84. Can we subtract 128? No, we can't. Okay, can we subtract 64? Yes, we can. Okay, so that gives us 20. Don't, there are animations on the slide. From 20, can we subtract 32? No, we can't. Can we subtract 16? Yes, we can. So that gives us 4 left over. And then we go, right, from 4, can we subtract 8? No, we can't. Can we subtract 4? Yes, we can. And that gives us 0 left over. Now, personally, this is the method that I prefer, but I am quite mathematically minded and I prefer to just sort of get it quick done and over with, um, just by sort of, I guess, brute forcing it in a way, right? You're just looking at the number and yeah, yeah, you're just sort of trying to force the answer out of it. I tend to use this sort of method for other uh, numerical systems as well, where I I don't know. I don't know. I don't necessarily have a good method that I follow. Um, I've I'm just fairly good at doing it. Um, but yeah, this is the one that I personally would prefer for binary, where you've got all your columns, you know what each column is worth. It's super easy for binary to know what each column is worth. Um, so just try subtracting those columns, and each time you can subtract it, then put a 1 in the column, and go through them one at a time to get your number. Um, I hope that was clear because I went on a bit of a tangent. So just to say that once again, we start with 84. We can't subtract 128 from 84. Can we subtract 64? Yes, we can. So we put a 1 in the 64's column and we subtract. That gives us 20 remaining. Then we say, can we subtract 32 from 20? No, we can't. So it gets a 0. What about 16? Yes, we can subtract 16 from 20. So we do that. That gets us 4 remaining. So we move on to the 8s. Can we subtract 8 from 4? No. Can we subtract 4 from 4? Yes. Okay, put a 1 there. And then we have 0 remaining. So the rest of our number is all zeros. So I hope that makes sense for people. Um, I'll give you a few examples to work through with that one as well. As I said, both of these values have merit, and I would heavily consider teaching both of them to your learners, unless you are sure that the class is going to work better with one method. Um, I think people just uh, th this is a topic that people don't like because we're all so comfortable with doing maths in decimal. And the fact that we're only taught decimal from primary school makes our brains hardwired to do decimal. Um, so when you start introducing these other number systems, people find it very complicated to begin with, to wrap their head around it. So I think offering multiple methods is very beneficial. Um, but that is up to you. Um, there you go. So here are these ones to have a go at. I'll leave you for a moment to get on with them. I'm glad this method's working better for you, Amwan. Um, Yeah, spot on. I was actually still writing that down. Yeah, so you got to that one before me. Um, I much prefer this method. Oh, you've done them all. Fantastic. Yeah, 65 looks right to me. Um, 65's a nice easy one. Good trick with them, right? As you know, 64 is one of the multiples of 2. So work out what the 64's column is, add zeros after it, put a 1 at the end. 134, going to be 164, yeah. Be 128. 128 plus a 2 plus a 4. Yeah, fabulous. Well done. So yeah, I much prefer that method. But if you've got someone that struggles with it, struggles to get their head around it, like actually writing it out slower, would quite possibly work a lot better for them. Okay. Um, well, it is 5 o'clock. Uh, yeah, that sums up binary. That's all we need to do on binary. Um, I'll do a quick introduction to hexadecimal. Um, but I also don't want to overload people in 1 week. Okay, we've done a lot of binary now, so I'll introduce hexadecimal, how it works, sort of the reason we use it, and I let Alex come back to the more complicated stuff around hexadecimal. Oh, actually, I think I'm doing next week anyway, so I'll come back to hexadecimal next week. Okay, so hexadecimal. It's another number system. This time it's base 16. So we have 16 symbols that make up the so it has 16 symbols. So the first 10 are made up of our usual number system, 0 to 9. And then we carry it on with the letters A, B, C, D, E, F. Okay. Now, people immediately don't like this. Okay. It looks like algebra. It's not algebra. Um, the symbols that we're using just represent numbers, further numbers in this system. As I said, we have grown up in a decimal world where we learn decimal since we're very, very young, and our brains are hardwired to do that. And so is our language and writing system. We don't have a symbol for the number 10. Okay, think about that. We don't have a symbol for the number 10. We use 10 because it is base 10. You count from 0 to 9, and then you go on to the next digit and you write 10, 11, 12, 13. So our digits only go up to 9, which means if we want to count in a higher base, we either have to invent some new symbols, um, which we could do. We could come up with entirely new number symbols, or we can sort of take the easy way out and just use letters because we've already got those symbols and we might as well use them. Um, However, interestingly, there are a decently sized group of people who very much want the world to convert to a base 12 number system, so that we should all stop using base 10 and instead use base 12, as I showed you with the finger counting earlier. Um, and in fact, we already do this. A lot of the maths that we use is based on base 12, right? We all know how to tell the time, use a clock. That's a that's well, it's not base 12 because it uses 10, 11, and 12 as the numbers. Um, but it essentially is base 12. Okay, we then have 60 minutes in an hour. We have 60 seconds in a minute. They're multiples of 12. Um, we use base 12 for angles. Okay, 360 is a multiple of 12. Um, the the base 12 numbers actually occupy a lot of the maths that we do. Um, the reason that people would want us to use base 12 is because it makes a lot of things easier. Okay, if you think of factors of the number 10. You've got 1, 2, 5, 10, which means it's easy to divide any base 10 number in half. It's easy to divide them into fifths. Okay, get 20% of something. It's easy to divide it by 10. It's not easy to do many other things with it. If you've got base 12, you can easily divide by 1, 2, 3, 4, 6, and 12. So it gives you more factors, makes it a nicer number system to use. Unfortunately, that's never going to happen because, as I said, we live in a base 10 world. You're not going to get 8 billion people to change to a new number system. It's not going to happen. But there are benefits to it. Anyway, hexadecimal uses 16 symbols, which we call 16 hex digits. Okay, so we start on 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So the number 15 in hexadecimal is F. If you were to write the number 15, you'd write F. The number 9 in hexadecimal is 9. The number 12 is C. The number 16 is F0, right? Just as when you get to 10, you go from 9, the last symbol in decimal, to 10. I just said F0, didn't I? I didn't mean F0. The number 16 in hexadecimal is 10, just as in decimal it becomes 10. However, the number 31 would be 1F. That's one of the big reasons we use hexadecimal, right? If you're using decimal, by the time you're at 31, you're already into the threes. You've counted past 10, you've counted past 20, you're now into your 30s. With hexadecimal, 31 is 1F. It's the final number of the tens. You shouldn't call them the tens. They're not the tens. But yeah, hexadecimal allows us to count very big numbers and conserve a lot of space because we have 16 digits to use. Now, converting from denary to hex, a good method of doing this is to remember the equivalent binary numbers for the first 16 hexadecimal digits. Okay, so 0 is all zeros in binary. 1 is 0001. 2 is 0010. 3, 0011. All the way up to 1111. And hopefully, if you're quite switched on and thinking about what we've just been talking about, then this is starting to make sense why we use hexadecimal in computing and in computer science. Because we can count up to 4 digits of binary with a single hexadecimal number. And that means we can reduce our machine code down to 1 digit, which makes it much nicer. We're not writing out binary all the time. But also, also it just pairs very, very nicely. Okay. The number 10 doesn't pair very nicely with binary because it's 1010. Whereas hexadecimal, what we've got here with the letter F, or sorry, the number F in hexadecimal, we've got a nibble. That's 4 bits, half a byte. which means you can represent a full byte in hexadecimal with two letters, two numbers. Sorry, I keep calling them letters. They're not letters. Okay, these are symbols for numbers. Okay, so how do we go about converting from denary to hex then? Well, we take our denary number, 13, we convert it into binary. So what have we got in denary? We've got 1, 8 in 13, we've got 1, 4, no 2s, and 1, 1. Okay, just using the method that we used last time. Or you can use the first method. Both are completely valid. But we get our binary value out of our denary value. And then that binary value is very easy to turn into hexadecimal. And if you do this a lot, if you practice this a lot, these numbers become second nature. Counting up to 16 in binary isn't particularly hard once you've done it a lot. Yeah, what 1110 is 14, and you just know that 1110 is 14. And so that makes that conversion very easy. Can anyone work out what 19 is in hexadecimal? Obviously, we're crossing over the threshold. We are going into our second units. Oh, ah, ooh, I'm not sure what they're called in hexadecimal. Um, our second column. We're going past our units. Okay, I'll move on. So to get this, well, in fact, yeah, I believe it's on the next slide. So since we have 19 and we know that 19 is more than the value of f is 15, we know that we're going to have to combine our hex digits here. I believe they may be called digits in the GCSE spec, so I won't correct that. However, like, yeah, bear in mind with that, unfortunately, a lot of the words that we use to refer to numbers are specific for decimal, because digit comes from a 4-bit binary number and is therefore more than a single hex digit. So we can split the binary digits into groups of 4, just like this. So we can add our zeros on the front, which makes it a bit easier for us to think about. So we've got 0, 0, 1, 1 is our first unit in hex, and 0, 0, 0, 1 at the start. And therefore, we just assign each of these groups of binary values their own digit, and that gives us 19 in decimal is 13 in hexadecimal. Remember what I said about not oh, sorry, I completely lost my train of thought. Not calling it 13. It's not 13. 13 is a decimal number. It is specifically a word for a decimal number. This is 13 hexadecimal. So yeah, hopefully you can see how that works. We've got 1111. No, we've got 0011 at the end, which is our 3. And then in front, we've just got a single 1. So that's the 1. So 1, 3 hexadecimal is the same as 19 decimal. Okay. And we got some more examples here. Okay. Turning 27 into binary gives us 11011. So we split that into 2. We get 1011 as our second, or our first digit rather, which is a B in hexadecimal. And then we've got 0001 in front. So 27 is 1B. We can make these bigger. 235 decimal works out as 11101011. So we split it after 4, which gives us 1011 in decimal, in 1011 in binary, which in hexadecimal is a B, and then 1110, which if we look up our hexadecimal table is E. So the number 235 decimal is EB in hexadecimal. And then similarly, we could take incredibly large numbers, which whoever made this PowerPoint gave up on even giving the decimal representation for this. 1100101101011010, which nicely, conveniently splits into 4 groups of. Oh no, it doesn't. That's 12 numbers long in binary. So we split it after 4 each time, making sure that we're working from the right-hand side, because that's where our number ends. Split it into groups of 4, which gives us 1010, which is an A in hexadecimal, 0110, a 6, 0001 is 1, and 0011 is 3. And so this very long binary number, which I'm not going to bother working out in decimal, you can do that for homework, is 316A in hexadecimal. And so if you'd like to have a go of working out those numbers, I can try and do, but here is make a table. Oh, this is not going to go well. That's not going to go well for you. You just have a quick Google for hexadecimal to binary. You can pull that table back up. Um, that'll make it easier for you to convert those. Fab. Well done, Amman. Yeah, you're spot on there. So the first one is C. Okay, when you got a nice small decimal number, you don't really have to go through the process converting it into binary first, okay, because you know that hexadecimal counts up to 16 or 15. Um, so you could just work that out straight off the bat. We don't have a symbol for 10, so that's A, 11 is B, so 12 is C. Um, 37 in decimal works out to 100101 in binary, which we split into four, gives us 0101, which is 5, and 0010, which is 2. So 2 5 hexadecimal is 37 in decimal. This one splits nicely. It's 10 in binary. Okay, this is the 8's column, this is the 2's column, so that's a 10, and same the other side, so AA. The fourth one is again splits here. That's so that's an A on this side, and on this side, sorry, I didn't get to work in this one out. We've got two, no, 1 5 13, which is um E in hexadecimal, so EA for number 4, I believe. And the final one is AF91, which I am just going to believe you there. And when, yeah, that's definitely a 1, that's a 9, that's an F, well done. And we got an A from before, fantastic. So yeah, that's hexadecimal. Fairly nice and easy to convert into hexadecimal. Um, obviously, as I said, hexadecimal is chosen because you can break down binary numbers into it so nicely. It makes it very, very useful for computer programming. And when you mentioned on one of the slides earlier about how one of the binaries worked out to 255, yeah, absolutely. So color values in programs are written from 0 to 255, right? 256, which is obviously a multiple of 2. So they are written in binary. There is 8 bits of binary, I believe, in 256. So it's a single byte is your color information. Whereas with hexadecimal, that 8-digit number of binary reduces to 2 letters of a hexadecimal code. So if you've seen hexadecimal colors before, because colors for computers are very often represented using hex values, they are eight digits long, which is your RGB values, red, green, and blue, and then brightness or white value or some other modifier in there with it. And so your eight number hexadecimal value would be a 32-digit binary value if you were to represent it that way instead. So when you're programming something and you want to quickly change the color of your graph or whatever, it's a lot nicer to go and look for the hex value and type that in than it is to look for a 32-bit binary number and try and type that in properly. So that's why hexadecimal is used. That's why it's important. I will stop there. That's a nice brief introduction to hexadecimal. Okay, we haven't got too complicated with it. Next week, we'll pick back up with this and look at how to convert back from hexadecimal into binary and decimal, and how we use shift functions and stuff of the sort. fabulous. So we'll end there. I hope everyone enjoyed. Um, and have a nice week. I'll see you next week.